All right, let's talk about probability. This concept is actually quite extensive. We spent all of December on all that time after Thanksgiving on this unit, and it takes a lot of practice to understand it and to get it. So, we are going to spend 2 days of our review time on this. It encompasses 10 to 20% of the exam, and it is likely that you're at least some part of a free response, if not all of it, will be related to probability. Okay, so let's get to some of the basic foundational ideas we learned first. The idea that two events happening, the probability of two events happening, if they are disjoint, also called mutually exclusive, then those things cannot happen at the same time. For example, if we were talking about you having turkey for Thanksgiving or having ham for Thanksgiving, then you could just add the probability of turkey plus the probability of ham because those are disjoint. So if two things are not overlapping, addition is easy. It's if you have overlap. And there were some people that had turkey and ham. If this was joint probability, then the addition component is a little bit more difficult because you're going to have add all of those who had turkey and you're going to add all of those who had ham, and some of them got double counted. And so that takes us to keeping track if you need the general addition rule. Let's go down to what it looks like on your formula chart. So here's the probability section. And we will talk about these binomials and actually the discrete random variables tomorrow. Okay, so we'll actually talk about this section tomorrow, but here we're going to be dealing with this today. And here is the general addition rule, this little part right here. This says that the probability of A, or, there's your union for or, is you can add the A portion plus the B portion. But see, if there's overlap, then you need to take away that part that got double counted. Okay, so there's that. Next, are events independent? Because this is going to play into how you can have two events occurring simultaneously, and if it changes the probability of the next event. So this affects our multiplication component. If I want this event to happen, and that's multiplication, this event to happen. So if they are independent, meaning the fact that this first thing has happened, you get your probability here. If the fact that that has happened and it hasn't changed, then the probability of it happening again, okay, is the same. But, of course, you need to pay attention to, has that probability changed? So is this second number different, conditional upon what happened first? Okay. So that plays into checking for independence, and do you have conditional probability? Did the fact that one thing happened affect the other? So let's take a look at that down here on your formulas. That is located here. Here is your conditional probability. Remember, this is red, the probability of A, given that B has happened. So we're saying out of all of the B's, what is the probability of A and B occurring? So this is your conditional to see, has the fact that B has happened changed that probability? And so then we'll see that whenever we're checking for independence. And this is something that I recommend you will add to your formula chart, or know this because it's not on the formula chart. This has to be known from your own brain. Okay. And here, if we are checking for that independence, where the fact that you are one thing is not changing the probability of the other, then this is specifically how we check for that. Is that overall that marginal, remember we had that a couple of days ago, that marginal probability of A happening, the same as the conditional of A happening given that B occurred. Are these two things equal? If these two computations are equal, then remember what that says. Given that B has occurred, it has not changed the probability of A. It's the same as overall. So therefore, we're saying that this marginal probability has not changed based on the condition that B occurred, and that would make the events A and B independent. Okay, and so that's how mathematically you can check for that. And so there we have that. Now, we'll come back and visit these geometric and binomial tomorrow. Geometric, you are going until your first success. And then, of course, binomial out of a set number of trials. How many successes do you expect? And so on. Again, talking about how many successes do you expect. Expected value is the mean. Expected value is the mean. And so we'll see that again. I'm just kind of planting that seed to remind you for tomorrow. Geometric 1 over p, binomial n times p. And so we'll talk about that tomorrow. I think the rest of this here is about geometric and binomial. Okay, so these probabilities, these definitions, these kind of come into play. We've already been talking about these. These make sense to us and common sense. One thing that you may not have mathematically remembered is that if they ask you for the probability of something happening once, or at least once, the probability that the event will happen at least once among the trials is, and this plays into the binomial idea, it's all the possible combinations that could possibly happen. Every single one, at least one. So 1 or 2 or 3 or 4, or however many successes. So there's at least one success. That's everything except for no successes. So the probability of at least one, if you are asked what's the probability that at least one thing will happen, then you know you want to do this without listing all those combinations, because that is not fun. There's way too many combinations that could happen. So therefore, it is easiest to compute this as 1 minus the probability that none of those events occur. All right, 1 minus the probability that none of those events occur. Here's some other information about what I was just talking about, our disjoints. Those two cannot happen at the same time. The probability of A and B is 0 because they are disjoint, so there is no A and B section. And if you know they're disjoint, then you can get out the easy way when you are adding those components together. If they are not disjoint, then we have that general addition rule. So here's this, and of course, you know your complement rule, and we've already talked about the independent. Now, remember, this is your or, your union, this or that, or both. That's the misconception. If they overlap, or can be this or that or both. Here is your and. This is them happening at the same time. And we organized all this information here in this thinking map, which I think will help you as you go through. Remember, is this an or problem? Are we asking for this or that? Well, then you need to see, is there overlap? Can those events happen at the same time? If they can happen at the same time, you have a little more complexity in how you compute, because you have to account for the overlap that would get double counted. If they do not overlap, then it is very simple to just add those two probabilities together. Now let's talk about the ands. This happening and that happening. That is this notation here. And ask yourself, do you know if these are independent? Does it say if they are independent? If it doesn't say that they are independent, then you've got to not make that assumption. We know how that assumption is not appropriate. But if they are independent, which is what I believe is mostly happening on your assignment today, it's tomorrow whenever we get into where they are not, then yes, we can just multiply this happening times the next one happening times the third one happening if you want it to happen multiple times, this and this and this and this, all multiplying together. If they are not, then we're getting more into that binomial situation where we have conditional probability. Now, one last technique and strategy that we talked about was a tree diagram. And so let's talk about when we use that. So you see we have all these multiple branches. Well, that is happening because you have several conditional probabilities. So here's what that will sound like. If the flight leaves on time, then the probability that the luggage does not get there is only 5%. But if the flight does not leave on time, then the probability the luggage doesn't get there is 25%. So see, if this happens, then, so conditional upon this happening, then here's some probabilities. But conditional upon this other event happening, here's some probabilities. So you have multiple event probabilities conditional upon other things. Then that's when your strategy, the tree diagram is the strategy for me. Do you have multiple conditional probabilities? Then that tree diagram is the strategy for me. All right. And so the best way to do this is to practice. I wanted to mention that when we did our problems that where we would have overlapping information, events, when we would have overlapping events. Some people found it helpful, and actually this is my go-to, is a Venn diagram such as this. But another technique I found some students wanting to use was making a two-way table out of the events. So, don't forget about that. If that was your technique of choice. So when you read a problem, and here's A, and so on and so forth. Okay, so as you go through reading the problems, remember, visualize it with Venn diagram or a two-way table. Remember if you're asking the ors or the ands. And don't forget about your conditional probability, multiple conditional probabilities. All right, that's it. You just have to practice, practice, practice. So I have got some of that for you there, pages 47 through 40. What is it, through 51, I believe, 47 to 51. Because see, then tomorrow we'll start getting into the geometric and the binomial. So you really need to spend the time going through these problems here on pages 47 through 51 today. All right, good luck to you on that.